But okay, so for this one, the curriculum is to essentially wrap up our polynomials stuff. So we're going to be looking at the sketching of cubics, quartics, and basically any of the other polynomials. We'll be then looking at how we can use those sketches to solve inequalities, and then we'll look at some of the applications of polynomials, which is namely going to be about figuring out the rule of a polynomial, and also how we can then apply it to like your real-world scenario type stuff. So we'll be looking at the screen share for those. Okay, first up, sketching cubics. So one of the first ways in which you are shown cubics is in this form here. It doesn't really have a name, so I've given it a name. I'm calling it the inflection point form, very similar to the turning point form that you would have on a quadratic. It works literally the exact same way, except what it is targeting is the inflection point of the cubic. So that thing there. The h and the k terms are responsible for the horizontal and the vertical translations of that term, of that graph rather. So this is the basic cubic. It kind of wobbles a little bit, starting at the bottom left and ending at the top right. Dilation factors work as they always have. Multiplications at the front will stretch it vertically. Bigger number means it will be closer to the y-axis. A number closer to 0 will make it go further away from the y-axis. You can see the distance between any given graph is increasing as this approaches 0. You typically don't get dilation factors split between horizontal and vertical simply because wherever you put it, you can always just factor it out and then combine it into one term. So while this is nominally a dilation factor along the y or from the x, it basically does both because any of them could be factored into each other. So you can see a little bit of an example there. This is where you would put an x dilate, but you could then just factor it out and then combine it into this term. Reflections, again, so negatives will cause it to flip. One of the interesting things about the cubic is it doesn't actually matter what type of reflection you have, the result will be the same. You will, instead of starting from the bottom left and ending at the top right, you will now start at the top left and end at the bottom right. This is referred to as the property that we're looking for here is called an odd function, right? Any function that has this sort of, I don't really know how else to describe it other than sort of like diagonal symmetry. You can see how it's like one thing here and then flipped in the other quadrant. If it has that sort of symmetry to it, then whatever reflection you apply, whether it's about the x or about the y, will be identical. Again, yeah, horizontal translations, just making sure that the negative does in fact move it right and the positive does in fact move it left. But this is the same as turning point form. So as long as you're confident with your quadratics turning point form, then all of these will be the same as if it was quadratics. Any questions about those fundamentals so far? Cool, okay. So what do we actually do to now sketch any given inflection point cubic? Well, we want to know where the axes intercepts are. If there's a restriction on the domain, we're also going to care about the endpoints of the graph. And the last key feature is going to be the inflection point. So here's an example. The easiest thing to do right off the rip is going to be to figure out where the inflection point is. So you can see this is a +1, so a shift left, and this is a -3, so a shift down by 3. That's going to give us a nice and easy inflection point. Axes intercepts are solved literally the same way as you always do. Y-axis intercept, you're going to set x equals 0. X-axis intercept, you're going to set y equals 0. The algebra is pretty easy for the y-axis. For the x-axis, you're going to be able to, well, you're going to have to figure out how to do your cubed roots. A lot of the time, that's not going to simplify into anything, so you do just leave it as a cubed root. But if for whatever reason you do get one that can be simplified, obviously you want to simplify that further. This was a bit of a simpler example. There is no domain restriction, so we're just going to put it all together. You can see the x-intercept, you can see the y-intercept, and their inflection point. Even if you forget what the curve should look like, even if you just dot out those things and draw a line connecting them, that should at least give you a pretty good head start as to finishing off the rest of the curve. So whether you remember this is bottom left and top right, dotting things out can lead you in the right direction. If we pretend that we had a restriction, so in this case from negative to inclusive to a half non-inclusive, we're just going to do the same thing we always do, which is sub in those endpoints and therefore get the corresponding y values so that we can finally just dot those out, making sure that we are using the correct dots here. So closed circle for inclusive, open circle for exclusive. Any questions about those so far? Okay. Factorized cubics, cool. So a lot of the time, probably most of the time actually, I would say the cubics are not going to be in an inflection point form. They're going to have a sequence of factors, such as this, right? Like a bunch of linear factors that are all back to back. There's a few things you want to consider when sketching factorized cubics. So you're going to consider what is the sign of the cubic? Is it an overall positive? Is it an overall negative? Do we have linear terms like that? That's a bunch of linear terms. Or do we have repeated linear terms, which would be something like this, where the linear has like a square on the top of it. That's just a bit of an overview. And in all those cases, we're just using that to solve for the axis intercept and the overall shape of the thing. Again, that's an overview. We'll look at the specific examples so you can see what that actually looks like. So here's one type of example you might come across. It's literally just a sequence of linear factors, and it is a net positive cubic. And the reason why we know it's positive is because all of the x's, when you do the sign analysis, like if you imagine expanding this out, positive, 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 it's going to be a net positive, right? That's just how multiplication and signs works out. Now, when it comes to linear factors, the solutions to those linear factors, like via null factor law, those are going to be the parts which the cubic cuts through the x-axis. So we're going to basically just go term by term, solve those, and those are not only going to be x-intercepts, but specifically they're going to cut through. So you can see it like starts from the bottom and ends at the top. It goes all the way through those spots. And you can see we have those sequence of cuts. Y-intercept, I mean, again, that's whatever, just x equals 0. Now, as for the overall shape bit, this is where knowing if it's positive or negative matters. Whether it's positive or negative works the exact same way as this cubic, the inflection point form, where positives will always start at the bottom left and end at the top right, and negatives will do the opposite. They'll start at the top left and end at the bottom right. So because we know it's positive, we know we're starting at the bottom left. So we start by drawing, and all you would do would be to dot out all the things you know. So you'd put like a mark there, there, and there, and just draw your curve connecting all those spots. That's all it is. That'll be basically the best you can do for now until we start looking at calculus. Calculus will help us to figure out where exactly to draw these turning points. But for now, you pretty much just eyeball it. There's no you could draw these quite high, you could draw these quite low. As long as you're hitting all the key features that we've solved so far, that's the main thing we're pointing out. I think that's what I mentioned here. Yeah, that's exactly what I mentioned there. Yeah, cool. Very similar example, but this time we have a negative cubic. Now, I have drawn it in a way that sort of hides it a little bit. Normally we think of negatives as having like a negative at the very front of the equation. However, when it's factorized, it can actually be in the factor itself. So in this case, we have a negative x and two positive x's. When you do the sign analysis of that, because you have a mismatch, there's more positives than negatives, or at least the mismatch like we're used to. It's going to come out net negative. Everything else is the same though. So x-intercepts, y-intercepts, you're solving by x equals 0 and y equals 0. They're still linear, so they're still just cuts, but the only thing that's happened differently now is because it was a net negative cubic, it's going to start top left, and it's going to end bottom right. That's those fundamentals so far. Any questions about that? Easy. Cool. Repeated linear factors. So again, this is where we have like a square on the linear term itself. X and Y intercepts are never going to change how you solve them. It's still just null factor law. But one of the things you'll notice is that instead of having 3 X intercepts, we now have 2. All right, and that's because, well, it looks like we just have 2 terms as opposed to 3 terms. What's different is that the solution to the squared linear term, or the repeated linear factor, is going to be a turning point on the x-axis, not a cut through it. So for instance, there's that -2 cut, but there's the +2 turn. It turns at that spot. So when you're doing your actual solution, you might just want to make a mental note that this one is a turning point. So you might just give it like a little TP on the as like a sign to make sure you turn at that spot. It should be kind of obvious anyway, because when you have 2 x-intercepts, you can't really draw 2 cuts, otherwise it looks like a quadratic. So you'll figure it out pretty rapidly whether you've got it right or not. Y-intercept, whatever. And this one, when you're counting if it's positive or negative, just remember that this one counts for 2. So this is a positive here, and it's 2 positives here. So that's 3 net positives. So we're going to have a positive cubic. Like for instance, if there was a negative in here, that will be a double negative, becomes back to a positive, and then this becomes a positive. So you just got to make sure that this one counts for 2 because it's squared. Positive means it starts bottom left, ends top right, and well, yeah, you can see exactly how that's panned out. Cuts at -2, comes back down to grab that y-intercept, and then turns here. Obviously, if you didn't turn, you would be continuing to draw it down here, and well, your cubic would look a bit weird because you're going to be like, hang on a minute, I've got to come back up, but there's nowhere to come back up because you don't have another factor. So these are things to consider when you're error checking the look of your graph. And here's the negative example. Again, I put it in the factor itself. It's kind of deceptive, so just keep in mind to look in here as well for your whether it's negative or positive. Other than that, nothing's really changing. So we're just going to start at the top left and at the bottom right instead of the reverse. And again, making sure that we're turning and cutting at the spots that should be turned and cutted through. Yeah, any questions on those ones? Easy. Rarely, you might get a quadratic factor in here, or more specifically, a quadratic that doesn't have a solution. Like for instance, x² + 1, there's no real solution to that, unless you want to do spec, in which case you have imaginary solutions or complex number solutions. That's not quite part of the curriculum for methods, though. The technical term for that is an irreducible quadratic term. You don't need to know that, though. All you need to know is that this contributes no x-intercepts. You only have 1 for this entire cubic. It is still a cubic, though, because you've got an x² and a -x over here. That would expand out to make a cubic. You've got a negative here, you've got a positive here. That's going to make a net negative thing. This is the worst kind of one to draw tech-free, because you kind of just got to, like we were kind of already freehanding the turning points. Now you just got to kind of freehand more or less the entire thing. So as long as you're cutting through the spots that you're supposed to cut through, the y and the x-intercept, namely, just draw a kind of wobble in it. That's really the best you can do without calculus at this point. Not that you would want to do anything with calculus here, because that would take quite a while. In fact, I think I even have an example here just to sort of show you the all of this effort in here would find a turning point. So this is really not something you do in a tech-free anyway. This would be much more supported by your CAS. But it is technically doable, just a lot of work. We won't go into too much detail for that, though. That's just sort of for later. That's cubics. Anything in there worth covering in any more detail?
Chris, could I ask what is like the actual inflection point like?
Yeah, so that is actually a really good question, because this wasn't something I was even overly familiar with until after school, which is funny. So an inflection point is just a point in which the graph wobbles. More specifically, it's when it goes from being concave down to concave up, So in this case, it would be considered concave. Hang on, what is this? Yeah, concave down. Oh, which one is it? This will be concave up because it's gone up. This is concave down because it's sort of curving down versus curving up. When you have a change between the way in which it's curving in or out to, that is an inflection point. That's any inflection point. When it comes to cubics, in specifically the inflection point form, we further state that this is a stationary point of inflection. And the difference there is that it becomes instantaneously flat at that spot. So its gradient would be 0. Kind of like this is how getting steeper and steeper. This is getting steeper and steeper. This is instantaneously flat at that spot. That's referred to as a stationary point of inflection.
And if we don't have the cubic in inflection point form, do we find it using a double derivative?
Derivative, can we do that? Yeah, so it'd be one of those scenarios where you're using your CAS anyway, because a lot of that would take a significant amount of effort. Like this one here does have an inflection point. Yeah, double derivative 0 will get you most of the way there. There are a few intricacies around specifically what the double derivative equals 0 gets you. It's in methods, it's by far just going to work pretty much every time. In Spec, there are a few extra considerations. Namely, I forget the specifics around like when it breaks, but rest assured in methods it pretty much never breaks. It's I think I detailed it in the notes on the stationary point stuff. Might have to revisit that though. But yeah, double derivative 0 should be perfectly fine for finding this.
How do you differentiate between a graph with a point of inflection and then a graph that has cuts and turning points?
Yeah, okay. So the only time it's ever going to do something like this is if it is all the way back here in the inflection point form, in which case that'll be fairly obvious. It's just the look of the function, or it'll look like where is it? Like this, where it's got a quadratic factor that gives no solutions. Those are the only 2 times in which you will get something like this. There's a bit more to it than that. This does not necessarily always mean that you'll get an inflection thing like that, which is kind of what I was talking about with this one being the worst one to do tech-free. There's so much that can go differently with this specific type of scenario that you kind of just got to do your best and draw enough of the graph. Everything except for this example here, and I've only got this in here simply because of completeness. This is something that very rarely gets touched on, maybe not even in the book. Everything else up until then is fairly standard, right? Like if you have linear, repeated linear, and they do have solutions, it's deterministic the entire way through. You know exactly what it's going to look like. Literally all of the key examples that can come up are in this document here. Is that a fair enough answer to the question? Cool. Okay, that's that. We're now going to expand that to more complicated, well, higher degree, higher order polynomials. First, we'll have a look at the difference between an odd and an even polynomial. That's not really a methods term, it's more so just what I'm using to describe the differences here. Most polynomials are going to have some type of form where it's either an inflection point form or a turning point form. They have some version of that. That's not to say everything can be converted into it, just there's typically the case where they can have some version of that. Anytime you have an odd power in here, what you're essentially going to have is a steeper and steeper cubic-like shape. You can see all of these are basically cubics, but they're just getting steeper and steeper as the powers get steeper. Any odd polynomial is, yeah, I shouldn't probably say that. This sort of function is described as an odd function as well, and any odd function has this this property here, which is to say that f of negative x is the same as negative f of x. This is more so as a very niche example that comes up in the textbooks, where you want to prove a function is odd or even. You pretty much just want to sub in negative x into your function, sub in negative as the like to get negative f, and see if they come out to be the same thing. So you do it in 2 stages. Do they look the same? If they do, congratulations, it's odd. What that means graphically is, let's pretend that x is 1. F of negative x would be f of negative 1, so down here. That should be the same as the negative of f of x. So f of 1 is up here, and negativing that would put it down here. And I mean, I'm kind of just eyeballing it, but you can see how that's what that graphically is actually representing. It just sort of got this diagonal symmetry to it. Even polynomials are ones where you have just even powers on that either turning point, the turning point form, basically. And they are just going to be steeper and steeper quadratics. There's a bit more flexibility with these. These can be vertically translated however you like, because even functions simply just have to be symmetrical either side of the y-axis. So any horizontal line is going to perfectly be equidistant from the center, no matter where you draw it. And as such, it can have any vertical translation. Odd functions are a lot more particular, because as soon as you shift this up even slightly, this would flip down to here, and you're just going to mismatch where you want it to actually match. So these sort of have to have exactly 0, 0 on them to be considered an odd function. Yep, that's just a bit about those. As for how that applies to sketching those types of polynomials, what we're essentially going to do is slightly expand on what we've already discussed. So we still know linear terms are just cuts. We knew repeated linear terms were turning points. We're going to slightly expand on that and say that actually any even power, so any of the 2, 4, any of those powers are also going to be turning points on the x-axis. And then as for the new thing we'll look at, any odd power, now specifically from the 3 onwards, because technically 1 is a power, but that would make it linear. Any odd power from 3 onwards would now be an inflection point, which should make at least a decent amount of sense, considering that x cubed would often have those sort of inflection points to them. So it's really just one more addition to that. We'll have a look at an example. This is not going to be anywhere in your book. The book caps out at quartics, so power 4. I'm just doing this to show you that even in extreme looking cases, it's good to be able to analyze what's likely to happen in the graph. X and Y intercepts, basically the same as always, just null factor law. This one had an odd power, this one had an even power. So remember that odd is going to be an inflection at that solution, and even is going to be a turning point at that solution. Then we just count positives and negatives. In this case, I've made it simple enough. They're all positive, so congrats. It's a positive, what is this, power 10? It's power 10. There's no real name for that. It's just a 10th degree polynomial. Now, specifically, you just want to make sure that because it is an even polynomial entirely, so it goes all the way up to power 10, it's going to have a quadratic-like shape to it, which means it's going to start and end at either the top or bottom, depending on if it was positive or negative. So, like, for instance, if we just have a look at all the examples here, the start and end is going to be the top because it's positive, or if you flipped it downwards, it would be either side in the negative spot. So that's what we have. You can see if you look at the outskirts of it, it's got that kind of quadratic shape. If you imagine connecting those, it has that parabola-like shape to it. It's going to inflect at the spot that we expect. It's going to have an extreme y-intercept all the way down there. So you can see the scale on these things can be ridiculous, but this is more so just for proof of concept. And yeah, it's going to have all those cuts, turns, and inflections at exactly what we expect them to. This, I mean, look, on the scale, this being negative 625, you can only imagine how high up these are. So you're never going to draw this tech-free, but it's a good skill to be able to look at a graph and understand what each of the factors are doing to that graph. Cool enough? Okay. This should be brief enough. We're going to have a look at how we can now use those graphs to solve inequalities. A lot of what you used to with inequalities would be like linear stuff, where you would just simply draw your equation and making sure that when you do your multiplications, you worry about whether it's positive, negative, whether you have to flip the sign or not. Problem is, when it gets to quadratics, you solve quadratics very differently to how you solve linear. Same with any other polynomial. And so you can't really just rearrange this thing and get x on its own. You'd have to do some sort of like quadratic formula to get there, and suddenly you're in a situation where you have to figure out, hang on a minute, how exactly does that play with the inequality? The answer is poorly. So we typically just ignore that approach entirely, and we just draw a graph. Because if you can get your inequality to be greater than, less than, whatever, to 0, like for instance here, rearranging this thing to be now less than 0, then all you have to do is sketch that inequality, sketch that quadratic that you have. Anywhere that it's above the x-axis is greater than 0. Anywhere that's below is less than 0. So you can ignore all the intricacies of all the complications that would come from here, and just look at that net quadratic or polynomial, sketch it exactly the same way you would always sketch it, and then look. In this case, we want to do a less than 0. So after having done all the effort to sketch that, we just see what are all the x values that have it below the x-axis. Below the x-axis. Starts here, ends here. Awesome. That's my solution range. If I want it to be above, I would say everything left of there and everything right of there. Very short thing. It's just using all the graphing stuff that we've just learned and then applying that to if you had an inequality. Cool? Okay. And lastly is the application. This is a fairly content-heavy class. Okay, so the first type of application you'll get are the families of function style questions. This is where you have a fully generic polynomial function, whatever type of function you have, and your goal is to figure out what all the coefficients are. When it comes to cubics specifically, we have all the different forms that we've discussed earlier. We didn't quite touch on this one, but this is just a generic polynomial form, just a sequence of x to the power of terms. You've got the factorized, you've got the inflection point form. Which form you use will depend on what information you have. You might already be familiar with how this works with quadratics. All right, you have your factorized, you have your turning point, and you have the polynomial form. This is something that would have been explored in year 11 as well. Okay, so if you have the inflection point and just any other point on the graph, you would want to start with the inflection point form, because the inflection point gives you not just one but two of the key features for that function. So it gives you, in this example, both the b and the c in this case. Now you've got one variable left, you've got 1 point left, match made in heaven. Just rearrange, solve, and then depending on what the question's asking you, you'll format your answer in a different way. This one was asking us for the equation, so we give the equation. If it's asking for a, b, and c, you would write at the end what a, b, and c are equal to. If you have a bunch of axes-intercepts, you would probably want to use the axes-intercept form. So we're cutting at 1, 2, and 3, so we're going to smash those out really quickly. X minus 1, X minus 2, X minus 3. Once again, you have A on its own. You'll pretty much always have A at the end, and you'll pretty much always have another point that you can sub in. Sub in that last point, do whatever arithmetic needs to be done, and that's going to get you your A. This is just sort of a combination of the two. We had a couple of axes intercepts, and we had a turning point as the key feature. This is the turning point. What am I saying? And so because we know that this axis intercept was the turning point, we can now make that the repeated linear term. So we're going to have the x plus 2 all squared for that one. And then everything else is the same. This may or may not have been a turning point. Kind of hard to tell with cubics. They can be quite a little bit lopsided. But yeah. And then lastly, if you have just any 4 random points, I'm sorry, my condolences, but doing this tech free is basically not going to happen. You're going to be doing a CAS instead, depending on what CAS you have. So this is TI Inspire syntax on, I know, yeah, I know your approach knows where the TI inspire stuff is. What CAS do you have, Raquel? Is that TI? Looks like TI. Yeah, that's TI. Cool. So you're going to be using menu algebra, solve system of equations. In fact, I can just bring it up on the document camera. Okay, so on the document camera, menu, algebra, solve system of equations, or 7 on mine, and then solve system of equations again. From here, it's just whatever, you know, plug in the number of equations you're supposed to have, and then label the variables as what you want them to be labeled. And then from there, yeah, you're just plugging in exactly the equations, just like you would for any simultaneous. Cool, all right, that's that type of question. Very similar to quadratics. Any questions about that so far? Okay. And the last type of question, finally, at the end almost, is the maximum or minimum style question. So you're trying to either find the max or the min of a certain quantity. In the case of polynomials, you're usually getting cubics, and you're probably doing stuff like volume. You would be used to, at this point, quadratics, where you're doing area. That's because you have a length and a width. Length times width, you have 2 dimensions. In volume, you have 3 dimensions. You need a cubic to represent that, usually. Or I guess I should say always. So the same approach that we use for solving the quadratic versions of those is the exact same approach we're going to use for solving the cubic versions. I've got all the steps detailed up here. Again, those can be looked at later. It's better we look at how those are actually applied to an example. So in this case, we have a square sheet of cardboard. We're told the length and width of it. We're told there are a bunch of cutouts from each of the corners, and it's folded up into a box. We want to maximize the volume of the box. This one didn't come with a picture. If you get a question that doesn't come with a picture, draw your own picture always, because it makes it a lot easier to know what's actually going on. Like, for instance, we weren't told what the size was that was cut out from each corner, but we know that they are equally sized, and we know that they are squares, so that makes it a lot easier to actually notate out what's happened in the diagram. From there, we can pretty easily recognize that 10 and 20 are no longer the full length and width, because we've actually cut out these spots here. So instead of just saying that the volume is length by width by height, well, that is still true, it is length by width by height, but we just need to update what the actual length and the actual height are by simply factoring in the fact that we've cut out 2 x's from either side. So we started at 20, cut out 2 x's, we started at 10, cut out 2 x's. As for the height, that takes a bit of visualization. Just imagine folding this sheet up, so you pretty much fold this inwards, and so on and so forth. If you're not familiar with how that works, literally just do that in your own time. Cut out a sheet of paper and then fold it up into a box. Very preschool stuff. Yeah, cool. And then just shove it all together. So length, width, height, all multiply together. You can do some further factorizing as well, just to make it a bit easier to see what each of those terms are. When you do this, you'll often have the sneaky looking thing where you have the negatives inside of the polynomial. So just keep that in mind when considering what's the overall shape. Fun fact, it's pretty much always going to look like this. Pretty much all the time, you're going to be narrowed in on this particular part of the cubic. I don't think I've ever seen it look any different to this, simply because as we explore this a little bit, there's really no other way it could look. But yeah, so if you just draw this as we've explored before, that's just a bunch of cuts at those spots. Keep in mind that this bit also is a factor as well. That x there does in fact mean you're cutting at 0. But this whole thing isn't valid. Reason why is because we have a volume graph. Volume is a real world quantity, so it should not ever have to be negative. So all of this below, invalid. And because this is invalid, this also has to be invalid, because if you have any lengths between here, well, that's also going to make this invalid. Also, since this is x on the x-axis, you can then sort of look back here and be like, hang on a minute, how big can x actually be? Like, can I cut out 10 from either side? Well, not quite. If I cut out 10 from this side, I can't do that from this side. So I'm actually capping out at 5 from this, 5 from this. I could do 10 from this, 10 from this, but since everything is sharing an x, that's not going to quite work out for all dimensions in there. So you've got to do a bit of critical thinking to figure out what's the actual valid domain. Or once you've seen it enough, you just realize it's always just this hump here. That's just pretty much what it always is. So that's a little cheat sheet thing for you. So sure enough, we get a little hump. You want the maximum? Well, there it is. So a lot of the time in polynomials, you're doing cas for this. So just use the fmax function. Probably be the best. No, I wouldn't. You probably want to graph it instead, and then have a look at this using the analyze graph tools. That, or you can fmax. It's fine. Just make sure you set your domain on it, and you kind of want that anyway because the analyze graph tool, so on the actual graph itself, will only ever give you a decimal value, and you need an exact a lot of the time. So I'll explore what fmax would actually look like. So if we go back to the document camera, I'll just draw just a basic quadratic x squared plus, I'll make it negative actually, so we can actually see the fmax. Cool. So we can see that the max should be there. If we did the analyze graph, we may or may not get something that we want. So if we go for maximum and grab that, well, that one gave us a nice enough answer. We could use that. A decent number of times is going to come out as a nasty decimal. So instead, what you would then go and do is open your calculator tool. If you've already drawn it on the cas, it'll actually have a name. So you can see that as f1 in the variable spot. What you're going to use is the fmax, which is calculus, and then down here, fmax. The syntax is to do function, comma, x, and if you leave it with no other parameters, it'll give you whatever the absolute maximum of the graph is, more specifically the x value of it. If there were other complications to it, like let's say this is now a cubic, what we would want would be that spot there, but if we then go and fmax this again, if it'll stop freezing, there we go, we get negative infinity, because what it's finding is the this bit over here. It's finding this tail. So once you figure out what your restriction on your domain is, you're now going to apply that. Whoops. You're now going to apply that to this. So in our case, we had 0 to 5. This is obviously not going to work because I'm using a different graph, but it'll illustrate enough for the point. 5, and you can see we get a very different outcome. We get the actual thing we were looking for. We can see that's 0.8-ish. This is also 0.8-ish. And then here's all you'd have to do if you were doing it tech-free. You'd have to use calculus derivative stuff. Yeah, just no, not happening. Cool. All right, there's one of the lengthiest lectures. Maybe I should split these up later. How was the pacing on that? Was that like information overload? That's good. Okay, nice. All right, so there was a lot there. As far as where that is in the textbook, that's from 4E all the way down, excluding, I think it's H. And we're excluding H just because this just doesn't really show up. Not much at all. Like it's looking at things like circle cuts and hyperbola cuts. It might be a SAC thing, so maybe consider having a look at it, but in a previous document I've shown you how to handle, or even in a previous class as well, if you want to look at the recording on that, it also covers this stuff. Rare though, so you probably only want to look at it if it comes up as something you're looking at in school. Okay, so there's a lot there. Is there anything in particular of those topics you guys want to have a look at? Because there's a lot. We're not going to cover nearly all of it. Happy to do any of it. Otherwise, I'll just pick maybe the applications. That's the hardest. Applications? Yeah. Okay. Let's see. Yeah, probably the hardest of the applications is going to be not where you're trying to do this sort of stuff, but where you're trying to do extended responses. Oh, actually, I should probably put the class plan in this one as well. So in the chat, that should be it. Whether you want to do it for homework or otherwise, is all the chapters and questions that were relevant to the stuff we've covered today. Do you have the Cambridge book, Raquel? Yeah, cool. Sweet. All right, let's crack into some extended responses. So let's have a look. Rate of flow of water is given by this equation. T is minutes. Find K. I'm not going to spend too much time talking about it. I'd rather let you guys just have a go, have a crack. Either go all the way to the answer and let me know, or if you want to talk your way through it, by all means, hop off mute and we can do that. So on to you guys. Oh, right, and because it's extended response, you do get CAS for this.
Is it 0.0011? I mean 12.
0.0012 is different to what I'm seeing. 0.0019 is what I'm seeing as a rounded bit. Do you have the fraction form? Maybe that's better.
20 on 16,875.
Yeah, this one says 4 on 3375.
Yeah, but that's the simplified version of the same fraction.
Oh, it is. Nice, okay. So I guess maybe the rounding looks a bit different. That or the answer looks different in here. Either way, yeah, it was just subbing in the point and solving for k, right? Any complications there? Let me know. Otherwise, part B, find the rate of flow.
Wait, Chris, what answer should we use? Like the one that I got or the one in the like on the textbook answers?
So you're saying that your CAS didn't simplify the fraction?
No, like okay, when I put 4 over 3375, I got 0.0012.
Oh yeah, there's just a typo in this. I think they forgot there was a 1 there and skipped over to the 8. Yeah, I think the answer in the book just has a bit of a typo. But did it ask for decimals? Hang on. Nah, so you want to give the fraction anyway. So it's kind of irrelevant. You just want to give the fraction.
What would you put in place of the lowercase r?
Place the lowercase r. Lower. Are you talking about this bit? That's a.
Oh wait, that's a t.
Yeah, that's a t.
Yeah, okay, awesome, thank you.
Yeah, that's fine. I'll Yeah, I don't know how zoomed out this is. There's only so far I can go into on the screen share. Might even be best if you guys have like your own copy of the book to look at. Is that fair? Yeah.
Chris, is this 11.85 mLs per minute?
0.85. Let me have a look. 320, 27. Yeah, that'll be right. Again, because it doesn't specify number of decimal places, you'd want to give that as the exact form. But yeah, that's fine. Cool. And yeah, that was just subbing in t equals 10, and you use the k from earlier that we've already found. Here's a new graph, and it's fully solved. We're still using the same k as earlier, I guess. Sketching, sure, it's nice to have that aid. I'm more interested in if you can... Oh, this is the same question, basically. Maybe get the graph going, but we'll have a look at... No, it's just the same question entirely. Okay, let's have a look at D instead. New equation, same k, and the same question again. Really? Okay. Never mind. Next up. Volume, sub in, sketch. Yeah, okay. I mean, this is slightly different. This time you're told volume and you have to find time. So maybe we'll skip all the way to 2c on this one here. And you can sketch if you want to get a picture of it. But otherwise, yeah, 2c. This one's going to be a bit of a mouthful, so if you want, you can give a rounded answer with decimals. You're going to have weird symbols in there as well.
3.96 hours.
Yeah, 3.96. Yeah, that was basically just the opposite. Instead of subbing in a t value, you're subbing in a volume value and then rearranging for t, or more specifically, you're CAS solving it because you have CAS. Let's see if we're given any volume when full is interesting because it's actually just a bit of reading comprehension. Let's see. We have a bowl. The volume is given by this. What's the volume when the bowl is full? Interesting wording of that. Not immediately obvious what that means. Let's see how you go. 3b. Pictures are going to be helpful for this one.
Is it going to be 144 pi?
44 pi is correct. Walk me through, or walk us through rather. How'd you get there?
It's a bowl,
Mhm.
and the radius is 6 centimeters.
Yep.
So I just subbed in 6 into the function.
Okay. Why does radius 6 mean 6 is okay? Because remember the x is actually a depth, not necessarily. But what's the relationship between the fact that it's depth and radius?
Okay, so a hemisphere is basically just like half of a sphere.
Yeah.
And when you picture a sphere, the radius goes to the center. So in this case, it'd be the top of the ball.
So the radius is in fact also the depth, the hemisphere part of it does imply that yes, that will also be 6. That gives you your x value. And once you know that, you're just subbing in x equals 6 and the rest of it's, yeah, rearranging or CAS. Clear enough there? Nice. Yeah, a bit of a fun one there. Not immediately obvious what to do. Depth and volume, we've already done something similar before. Here's a new picture. We want to cut a cylinder out of a... What? Cutting a circular cylinder out of a sphere. Cross-section of the sphere and cylinder. Okay, I mean I was seeing a circle. Which one's which? What?
Shouldn't both the cross sections be circular?
I mean, yeah. Hang on. So we're cutting a circular cylinder from a solid sphere. So let's say I'm going to try and draw my own picture for this just to get a better idea of what I'm looking at. So this is going to be a top down of the sphere, and you want to cut a cylinder, circular cylinder from that. So at least it's got to be smaller. And then the cross section of the sphere and cylinder section of the sphere and cylinder. I don't know about that one. The picture seems off. Why would it be a square? I mean, I can kind of imagine why, because they're trying to like maximize how much they can take out of it. And if you imagine, do I have anything sphere shaped? Kind of. Yeah, like if you could imagine trying to, for instance, take as much of a cylinder out of this as possible, you'd want to cut like on each of these corners as the maximum you could take out of it. And I think that's what they're trying to describe with like the blue square in the picture there, to maximize how much of a circle you could take out of this. This isn't a circle, obviously, so it's going to look a bit weird, but... Oh, actually, hang on, here's a circle thing. But I need a cylinder. A sphere, rather. Yeah, never mind, that's not going to work either. Point is, to maximize it, you'd be cutting at the quote-unquote corners of a sphere, which is, I think, what they're trying to get at there. Let's see how much it matters. I mean, they've kind of already written all the terms here, so it might not matter too much. Express r in terms of h. R is the radius of the cylinder. H is the height of the cylinder. Yeah, okay. And show that the volume. Oh, I guess it's the side profile, so you would see it as a square anyway. Yeah, okay. Hence show that this is our volume. So for that, you would probably need the equation for volume of cylinder. Do we have that? Probably not. Does anyone remember the volume equation of the cylinder? Or do I need to pull that up? Because I don't remember it.
It's the volume of a cylinder is pi times r squared times h.
Right. R squared h. Yeah, that sounds about right. Cool. Okay, so that should help us out. We got R, we got H, or at least they're written in there. We got to do a bit of math to figure out getting R in terms of H, and then basically from there it's just rearranging. So, you know, with these show that style questions, you're not allowed to start with the equation and then go back, but you can look at it and be like, okay, where is this likely to have come from? And then you can kind of use it to get your way there. So yeah, the first goal is going to be to figure out how we're going to get r in terms of h here. Once you do that, the rest of it should fall in place. Probably on the trickier side, maybe the hardest one we've done the lesson. Especially considering I spent like a minute or so trying to figure out what the picture looked like. Have you got a lead that you're following, or would you like a hint? A hint? Yeah. Looking at, so if we have a look at like my handwritten bit, the poorly drawn version of that, one thing I would consider would be the immediate relationship between r and h, but also how r has an equivalent horizontal distance here. The other thing to consider is that this is the origin, so either side of that origin is going to be 50-50, which will help you get a relationship between h and r. And, well, one thing that's starting to become a bit more obvious is that you have a right angle triangle that you can work with from here. Reckon that's enough to go off of in about a minute or so? We go over a little bit, it's fine. But sing out if you're still lost afterwards.
I substituted my value for r into the equation, but then going on from that got stuck.
So when you said you subbed in a value of r, what'd you sub in?
Would r be 2 over h?
H. So it's kind of, would r be 2 over h? Does that
Because
work?
isn't
H
h
is
equal to 2r?
yeah. Hang on. Yeah, that's good. Yeah, you're right. I had it the other way in my head. H is 2 r's. Yeah. So H is 2 r, and then r is H on 2.
Wait. Yes. Yeah.
Okay, that's what was going off then. Yeah.
Okay, yeah, I understand what I'm doing now.
Awesome.
How does the 100 come into it?
How does the 100 come into it? Let's see. Where's that 100 from? From here. Okay. So I guess how far have you gotten so far? Have you got like a rearranged R?
Yeah, so I've got the rearranged r, and then I put that value into the equation for volume of the cylinder.
Okay. So
And
first
then
let's just make sure the R's right. So what do you get for R?
h on 2.
Oh. Oh, okay. Oh, have I misunderstood this? H on 2. Hang on. Yeah, I've made a bit of a mistake there. So I probably shouldn't have said quite like that. Yeah, no, that's wrong. Reason why is because if we actually have a look at what's happening in the right angle triangle, you got R, you got the H on 2 is fine here. What we're essentially doing is Pythag between these two. So I think what I'll do to make it a bit clearer is get up the solution doc here, which is now showing. Yes, okay. So we're creating the Pythag equation, and that's how they then got their R from there. So you got H on 2 for this side of it, you got R for this side of it. Now why are they not the same? R is from there to there, H on 2 is from there to there. Why is that not just R is H on 2? Because H is this entire length, whereas R is that. Why are they not just that? I mean, maybe the pictures, I mean, we kind of had a few issues with the picture before. Maybe something about the scale of it just seems off. Maybe this is not actually a square. Did they even say it's a square? All right, it's a cross section. It doesn't necessarily have to be a square. It would just be any sort of rectangle. So it might just be the scale of what's being looked at is not in fact a square, and that's why it's not. You can't really just say R is H on 2. Yeah, maybe it was that. That would be probably the only explanation for it. I can't imagine why it otherwise wouldn't be. So yeah. weird picture. I'm going to just sort of chalk it up to that. If it was more obvious that this was like elongated, then none of us would have made that mistake. And the Pythag approach would have been more or less obvious at that point, you reckon? Like using the Pythag equation, you know this one, and you got this here. So you just do Pythagoras, a squared plus b squared equals c squared. And then you
But would it still be h on 2 then? It was
well, no, because like if I draw a different version of this, for instance, where the rectangle is clearly a rectangle, you have this was called R, this thing was called H. You can now see H on 2 is not going to be the same as R. It's just that it looked like a square in our picture. It was slightly rectangular.
So how would you work out that other value then?
Yeah, so we're using Pythagoras. So you've got 5 squared is the same as R squared plus H on 2 squared. And you're just rearranging one or the other for... We wanted to get R in terms of H, so we rearranged to get R on its own.
Oh, so the value would still be H on 2. It just wouldn't be equal to R.
Yeah, it's just that they wouldn't be the same as each other.
Sense.
Yeah, that's what I meant by that. And then from there, yeah, if we even saw in the solution that once you rearrange that, you do get that 100 and the square root that we were looking for. Cool. All right, finish off with the tough one. But yeah, there's a solution in there, and yeah, clear enough now? Cool. All right, that has brought us to the end of the class on that one. The next class that's available to you is the Friday. So nominally the way these sort of work is typically class 1 will do Unit 1 and 2 stuff, class 2 will do Unit 3, 4 stuff, and then the Friday is the catch-up we just go through the same content on that class. Again, the primary thing is to go through anyone's specific questions if they have them. So that's just sort of like a fallback. We do that when no one else has anything they want to particularly look at. So if you do have things you're looking at, like I think you guys did hyperbolas or something last time. If you're still wanting to look at that, feel free to submit that for class 3 and I'm more than happy to go through that. Are you free for the Friday?
Yeah, I am.
Yeah, easy. Cool. So if you want to go through that, feel free to submit that. Otherwise, it'll just be a repeat of this sort of stuff. We can keep going to like question 5 and beyond. Cool. All right, I'll leave you to it.
Awesome. Thank you.
Thank you.